Okay, so we are continuing with bivariate distributions, and at the end of the last video, I asked you to try to tackle the variance of y, which is part 3c here, and to try to figure out the correlation between x and y, which is part d. And I gave you some extra time in order to work on these. So I was talking about the variance of y. You get the second moment to be 1/2, which I show on the bottom left. And then using that, the second moment minus the square of the first moment, which was 2/3 according to part B. And this is, first moment is the mean of y. And so 1/2 minus 2/3 squared simplifies to 1/18. And so it just happens for this problem that the variance of x and the variance of y are the same value. It's not a pattern. It's not required for all problems. But for this one, it is. So then you may have made some progress in part D. I'll go ahead and talk about that. If you're still working on it, it's fine. So in part D, we are, we are trying to find the correlation, which means we need to find all the pieces for this formula I have written on the left side of D, which is the expected value of xy, which we haven't found yet, minus the expected value of x times the expected value of y, which is the product of the means, which we got in part B, divide by the standard deviations of x and y, which are the square roots of what we just got in part C. So we have most of it except for e of xy. So below that in blue, I show the derivation for that expected value. So it's a double integral of xy times the joint PDF of 2. I decide to integrate with respect to y first and x second. And so since it's y first, y is, again, looking at the support between x and 1, and then x will be between 0 and 1. So that's just my preference. You could have integrated x first, but then you'd have to make sure you have the right limits of integration. So integrating y first, y becomes y squared over 2, which cancels out the 2's. You have an x times y squared. Y squared is evaluated from x to 1. So that's going to give you a 1 minus x squared times the x out front, which is where my x minus x cubed comes from. And now when you integrate this, you get x squared over 2 minus x to the 4th over 4. And you evaluate that from 0 to 1, which gives you a 1/2 minus a 4th, which gives you a 4th. And this is, so I'm looking right here, that is your expected value of xy, which you then go plug in to the top left of the formula. And so you have 1/4 minus the product of 1/3 and 2/3. Remember that's the mean of your x and your mean of y. Divide by the square root of the variances in order to get your standard deviations. I wrote it in the variance form because the answer stands out pretty easily. The square root of 1/18 times 1/18, or the square root of 1/18 squared, is just 1/18. And then this happens to simplify nicely to 1/2. And so this is our correlation, which you could report as a fraction, or you could report as 0.5. Either is fine. So, questions on part C or D?
You know, for e of x, y, why is it one of the intervals like x to 1 and the other one 0 to 1? Like not, it doesn't have y in it.
Remember, you are integrating this joint PDF, which has support that 0 is less than x, which is less than y, which is less than 1. So when you're integrating, as I did, y first, which is dependent on x, you have to account for that. So y is between x and 1. And then x will be between 0 and 1. If you decide to integrate x first, so I'll do that basic setup over here. So if you were doing dx dy, then x is bounded by 0 and y, and y will be bounded by 0 and 1 after you've integrated x out. And so being that your supports have x and y dependent on one another, you need to account for that in your bounds, your limits of integration.
So the first one you integrate has to have the other variable in it?
Because the supports are dependent on each other. It's more important to understand it that way than it is to try to view it as an algorithm. Let me look back. You know what? The next problem might show you a case where the first variable being integrated does not depend on the second one. So let's take a look at that, and maybe it answers whatever confusion you have lingering. So in number 4, which I didn't ask you to tackle, but if you did, that's fine. We want to consider the joint PDF that's given. And this notation doesn't mean that x is greater than or equal to 0 and y is less than or equal to 1. It means that x and y are both between 0 and 1 or equal to. And so that's a joint support. And that's how you interpret that one. But there's no insinuation of x and y being related. So we don't know if x is always less than y or y is always less than x. None of that is implied by this particular domain. We want to know the probability that y is less than or equal to x over 2. So here we've got our joint PDF of 4/3 times 1 minus xy. I'm going to integrate y first. And in this case, it's because I know y is restricted by x, not because of the support, but because of the probability statement. The probability statement says we want the probability that y is less than or equal to x over 2. So I know that this upper bound is x over 2, and I know the smallest y can be is 0. As far as x goes, there's no restriction on that, so that's going to go from 0 to 1. And this is what we want to integrate in order to get our answer. So from here, you always do the inner integral first. So we have 4/3 integrating with respect to y. We have y minus x y squared over 2. And y is being evaluated from 0 to x over 2. So we've got that 4/3, which is constant. I'm just going to pull it out. Evaluating that integrand over those limits of integration, y is going to be x over 2 minus 0 minus the x times x over 2 squared, which is x squared over 4, times the x over 2 up front is going to be x cubed over 8 dx. And so that's what the integrand becomes when we actually evaluate from 0 to x over 2. Now we have a polynomial. We're integrating with respect to x. So we've got 4/3 out front. This is going to be x squared over 4 minus x to the 4th over 32, which we are evaluating from 0 to 1. So that gives us 4/3 times 1/4 minus 1/32. And if you get a common denominator, that 1/4 is going to be 8 over 32 minus the 1 over 32, which is 7 over 32. The 4 goes into 32 8 times, and we get 7/24. Rich, remember, this is a probability, so it has to satisfy being some value equal to or between 0 and 1, which it is. It's a positive fraction less than 1. And so it seems reasonable, and that's our answer.
For this one, so I know you were saying earlier that if you're doing the double integral stuff, the first one has to have the variable because the other one depends on it or something.
Well, that was because in problem 3, the support says that they depend on one another. In problem 4, the question at hand, the probability statement, says that they depend on one another.
But it's between, but X and Y, are they they're both between 0 and 1. But
it doesn't,
you don't know what's one.
It doesn't say that one must be less than or equal to the other. You just know that they're both between 0 and 1 or equal to.
So how do you know that Y is between 0 and X divided by 2?
So I know that it's greater than 0 because of the support.
Yeah.
I know that it's less than X over 2 because of the probability we want to find.
Oh. Okay.
Is there a part B? Yes. All right. Any other questions before we move on to B? All right, let's take a look at B then. It's still pertaining to the same problem. Here we want to know the probability that X is less than a half and Y is greater than 0.75, 3/4. So let's set this up. This is a joint or a double integral of 4/3 1 minus xy. I'm going to do y first, x second, again, just my preference. And so y has to be greater than 0.75, so that's going to go from 3/4 up to the max of the support, which is 1. Y is going to start from the bottom of the support, 0, and go up to what value? Sorry, x. X starts at 0 and goes up to what value?
1/2.
1/2 or 0.5. And so this is the integral that you want to evaluate. So I'm going to give a few minutes here for you guys to actually evaluate this integral and get an answer. I'm going to pause the recording, and then we'll return when I think you've had a sufficient amount of time. Okay, so from the chat board on the side, it looks like a number of you got the answer 25 divided by 192, which is 0.1302 in decimal form. And that's what I got. So let me go through and just demonstrate how to progress from the integral that we set up together. So you're integrating the inner integral first. So we've got 0 to the half as the limits of the outer integral, then 4/3, and the integral with respect to y is going to be y minus x y squared over 2. Y is being evaluated from 3/4 up to 1, and then we'll be integrating with respect to x. But before we do that, let's solidify what this is after we evaluate with respect to y. And the y is going to be 1 minus 3/4, which is 1/4, minus x times 1 squared over 2, or 1/2, minus 3/4 squared over 2, which is going to be 9/32. So that's going to be 1/2 minus 9/32. And we could simplify that a little bit, getting a common denominator. That is going to be 7/32. So this gives us the integral 0 to 1/2, 4/3 times 1/4 minus 7x/32. And we could simplify a little bit further by realizing that the 4 in the numerator outside simplifies what's inside the parentheses a little bit. This is going to become a 1 for the first term and an 8 in the denominator of the second. So when we integrate this, we're going to have a 1/3 out front. The 1 becomes x, and then the 7x/8 becomes 7x² over 16. And that is being evaluated from 0 to 1/2. So we've got 1/3. X is 1/2 minus 0, which is 1/2, minus 7/16 times 1/2 squared minus 0 squared, which is 1/4. And then when we get common denominator for the inside, that is going to be, let's see, 64. It's going to be 64. So we've got 32 minus 7, which is going to be 1/3 times 25 over 64, which is 25 over 192, which, as I said earlier, is 0.1302. And for me, it doesn't matter whether you report it in fractional form or decimal. Decimal form for probabilities is pretty common, and 4 decimal places is a good rule of thumb. But that is our answer. Any questions on any step through this integration process? There's 2 more parts to this handout, but I just want to make sure that we're all together before we continue on. Okay, so it seems like it's all good. So the next part wants the marginal distribution of y, which means we want to get a function of y only. Because this is a continuous joint PDF, we need to integrate out x, the other variable. So that means that f of y is going to be given by integrating out 4/3 1 minus xy dx, integrating x, and x goes from 0 to 1. So this is what we want to solve for in order to get a function of y only, because this is only going to end up making x disappear and that y is going to remain. So again, I am going to pause the video. I'll give you a few minutes in order to do this. And actually, before we do that, let's set up part D just so you could tackle both at the same time. Part D is going to want you to derive the mean of x. So this means we want the expected value of x. And the expected value is the double integral of x times the joint PDF, which is 4/3, 1 minus xy, dy dx, or you could do dx dy. The order actually doesn't matter in this case. 0 to 1 for the limits of integration for both variables. And this is what you're going to want to evaluate for part D. And so again, I'm going to pause the video. I'm going to give you some time to try to get answers for both of part C and D in this problem. All right, so you've had some time to work on both parts C and D, and based on the chat board, there were a number of people that were getting at least one or the other. Hopefully a good group were getting both. So let me go through how to solve each of them after we set up the integral for each, and I'll do part C first. So in C, here we are integrating with respect to only x because we want a function of y in the end. So y shouldn't disappear. When we integrate with respect to x, we've got x minus x squared y over 2. And we are evaluating x from 0 to 1, which is going to give us 4/3. X goes 1 minus 0, which is 1, minus the x squared is 1 squared minus 0 squared, which is still 1, times y over 2. And the support is still y is somewhere between 0 and 1. So I know from the chat board, at least some of you multiplied to 4/3 through, and that's fine. There's nothing wrong with that. I think it looks a little nicer to keep it out, but either path is fine. I mean, both functions are equivalent. And so this is what you should get for part C. If you're finding that you tend to be making things harder than they are, then just be careful. If you're finding that you're struggling with basic integration like this example calls for, then please go and review your integration, because that's going to persist for a number of weeks. For part D, again, you could actually integrate x first, then y. The order doesn't matter here because the limits of integration aren't dependent on the other variable. But I'll just stick with the order that I wrote it in. So I'm going to integrate y first, which inside is going to give us 4/3 x y minus x y squared over 2, where y is being evaluated from 0 to 1. So this simplifies to 4/3 x, and y is going to be 1 minus 0, which is 1, minus x over 2. Y squared is 1 squared minus 0 squared, which is 1. And so this is the function that we're integrating with respect to x. And when we do that, we get 4/3. X becomes x squared over 2, minus the x squared over 2 becomes x cubed over 6. And that is being evaluated from 0 to 1, which gives us 4/3 times 1/2 minus 1/6. The 1/2 minus 1/6, the 1/2 is 3/6 minus 1/6, which is 2/6 or 1/3, which gives you 4/9, or 0.4444 repeating. And that is the mean of x. So this concludes the introduction to this bivariate handout. We're about to move on to conditional distributions, conditional probability, conditional expectation, so everything conditional. Before we do that, any questions on this handout? Okay, so again, I'm going to trust the silence means that you guys feel pretty strong and that you're ready to move on to something a little different. So that brings us to conditional distributions. Now, from this point on, I'm tackling discrete and continuous simultaneously, just as you saw in the last handout. And so here you have seen conditional probability before. Conditional distribution is going to feel kind of similar in notation. So remember, with conditional probability, you had the probability of A given B is the probability of A and B over the probability of B, or namely the form that you guys had seen was the probability of A given B equals the probability of A and B over the probability of B. And so that was back in like week 1 or 2. The form here is similar. You've got the conditional probability is equal to the joint probability on top over the marginal distribution on bottom, and that's the marginal of what you are conditioning on. So x given y has p of y on the bottom. If it were y given x, it would have p of x on the bottom. And likewise, for the continuous case, you would have f of y if you're conditioning on y, you'd have f of x if you're conditioning on x. And so that pattern is the same as what you should be used to. Manipulations are really going to depend on the exact conditions that you're finding probabilities for. And so it's at this point that I think actually going through example problems is really going to start to make things stand out. So let's jump into problem 1 here. It says, let the joint PMF of x and y be defined as the following. Pxy is x plus y over 21, where x can be 1, 2, and 3, and y can be 1 and 2. So you saw this on the last handout. We're just doing something different with it. For the first part, we want to find the probability that y equals 2, given that x equals 2. So let's first set up the conditional probability of y given x. According to the notation above, this is the probability of x and y over the probability of x, which means that the numerator is x plus y over 21, and the denominator is px, which, to save time, let's actually look back at that handout. We got p of x to be 2x plus 3 over 21. And so again, this is the last handout that we just finished. It's the same problem, we're just doing something else with it, but the information will come out the same. So the marginal distribution of x is 2x plus 3 all over 21. So I'm going to plug that in. 2x plus 3 over 21. And when you simplify this, you get x plus y all over 2x plus 3. And so this is our conditional distribution of y given x. Now, what changes here is that the probability that y is 2 given that x is 2 is you have explicit values for each of x and y. And so you're going to plug each in appropriately. So x is 2, y is 2, The bottom, you've got 2 times an x value of 2 plus 3. So you get 4 over 7, and that's your answer. So it seems fairly straightforward. There shouldn't have been anything that is unexpected. Where the unexpected might come in is with the second case, part 2. So let's go ahead and take a look at that. So in part 2 now, we want the probability that y is 2 given that x is less than or equal to 2. So over here, this is the probability that y is 2 given that x is less than or equal to 2. By definition, this is the probability that y is 2 and x is less than or equal to 2 over the probability that x is less than or equal to 2. So the numerator corresponds to our summation for x. Remember, x can take the values 1, 2, and 3, except x is bounded above by 2, so it could be 1 and 2. And we have the joint distribution of x plus y over 21, but y is 2. So I'm going to let y be 2 there. And this summation is our numerator. The denominator is going to be using our marginal distribution of x, which was 2x plus 3 over 21. And x, again, is bounded above by 2, so it goes from 1 to 2. So for this problem, because we have an interval, at least with respect to the x variable, we have to actually get the numerator and the denominator separately. So let's go ahead and evaluate them. So on top, you're going to get 1 plus 2, which is 321, plus when x is 2, you get 2 plus 2, or 4 over 21, divided by, on the bottom, when x is 1, you get 5 over 21, plus when x is 2, you get 7 over 21. So our numerator is going to be 7 over 21, and the denominator is 12 over 21, which means that our answer is 7/12. So it's just the first problem. And there's plenty more to do, but I just wanted to start giving you a taste so that you could see that there are differences depending on whether you are finding strict equalities in terms of your probabilities or you have a range for at least one of the variables. So let's continue. Yes?
Sorry. A question, just a kind of quick question about P of X. What was it? 2x plus 3 or 21?
We got that from problem 1 on the last handout. It's the same distribution. Rather than rederive the marginal distribution of x, I just took it from what we found earlier.
Oh, it was the marginal?
Yeah, that's what P is.
Oh, yeah. Okay.
Were there any other questions?
I have a question for part 1.
Okay, and let me just Go back.
Oh,
Okay.
Yeah, the problem was P of y given x. So why did you put the second part as P of x comma y instead of P of y comma x over P of y?
You're talking about here?
Yeah, as opposed to like part 2 where you put P of y equal to 2 comma x.
It actually doesn't matter the order there. So P of xy is the same as P of yx. So I could write this as P of x less than or equal to 2, comma P of x less than or equal to 2, comma y equals 2. So the order in the joint distribution doesn't matter.
Okay.
It does matter in conditional. Probability of y equal to given x less than or equal to 2 is not necessarily the same as the probability of x less than or equal to 2 given that y equals 2.
Okay.
Anyone else? All right, let's take a look at problem 2 then. So here we have f of x is 1/10, where x is discrete. So x can be 0, 1, 2, 3, 4, up through 9. And h of y given x is 1 over 10 minus x, where y is a function of x. Y equals x plus 1, up through 9. So in other words, if x is 0, then y is 0 up through 9. If x is 4, then y is 4, 5, 6, 7, 8, 9, and so forth. So we want to find the joint distribution of x and y. By definition, this is going to be, let's see, the probability of y given x times the probability of x. And so this is just manipulating this relationship here to find the joint distribution. Now in this case, our conditional and our marginal were given slightly different notation. And so the conditional is h of y given x. And the marginal is f of x. Which means when I plug in and I solve, I get 1 over 10 times 10 minus x. Where x goes from 0 to 9, and y goes from x up to 9. And that's the answer. In part B, it's implying that here we want to find the marginal distribution of y. Being that these are discrete distributions, that means we're going to sum out x. So g of y is going to be the sum as x goes from 0 to 9 of our joint distribution, 1 over 10, 10 minus x. So I'm going to pull a 1/10 out just to make it a little cleaner, which means I'm going to evaluate 1 over 10 minus x as x goes from 0 to 9. So when it's 0, this is 1/10. When it's 1, this is 1/9. And when it's 9, it's 1. And so this is this is the distribution, or sorry, this is our marginal distribution of y. We could try to evaluate this and see what we get. So 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/10 divided by 10 is, and I'll put this in decimal form, it's about 0.2929. Oh, I already divided by 10. And so that is the marginal distribution of y. And the support let me just think about this for a moment. Okay, so thanks for your patience. What happened was, with part B, we got an answer by adding across all x values, which based on the definition of the marginal distribution is what you should be doing. But then y is still in terms of x. The support of y is still in terms of x. But after we've added x out, I mean, we've already accounted for when x is 0, 1, 2, 3, 4, up through 9. And so it wasn't clear to me which x value to use in its entirety, because we've already used all the x's. And so that's why it made me hesitate, and I had to figure out, okay, well, something feels off with what I've written in part B so far. So that's how I noticed that I seem to have an issue. And so I went down for more space just to not be restricted in my thoughts. I did two things. The first was I checked that my joint distribution was valid. So that's what I have on top. I knew that if it was written correctly, then the sum, or double sum in this case, has to equal 1, and it did. So that brought me comfort. There wasn't a mistake in the previous part. And then I had to think through what happens as I sum x out. And so I noticed that when x was 0, I had 1 over 100. When x was 1, I had 1 over 90, and so forth. but my y was changing because y, when x was 0, went from 0 to 9. When x was 1, it went from 1 to 9, and so forth. So the multiplier went from 10, 9, 8, 7, 6, 5, all the way down to 1. So then I realized, okay, it's easiest, rather than to try to think of a single function term that g of y is, to view it as a piecewise function, which is what I wrote next. And I realized, well, when y can be 0 through 9, which is when x is 0, that probability, or the PMF, is 1 over 100. And it's 1 over 90 when y is 1 to 9, 1 over 80 when y is 2 to 9, and so forth. But then I recognized that if I were to sum each piece, that y going from 0 to 9 at a value of 1 over 100, remember this is a PMF, that's going to simplify to 1/10. And then when y goes from 1 to 9, which is when x is 1, that's going to simplify to 1/10 also. And so is the next one, and the next sum, and the next sum. And so I could view this as 1/10 when y is 0, when it's 1, when it's 2, 3, 4, up through 9. And if you don't see it, you could always check, is summing 1/10 from 0 to 9 going to give you 1? And it does. And so that was the thought process that I went through. Alvin, was that helpful? All right, good. So let me just write that back in the part over here. And I'll just make a note, C work at bottom. So that is our answer to part B. Slightly tricky one, but that's how I recognized that something seemed to be off. The other thing was I have my solution and I saw that somehow I got 1/10, but I didn't write enough notes in it to realize how I got there. So I just had to think it through again. And then problem 3 is like one that we've seen before, but we're finding a probability that we haven't worked through. So this is a continuous distribution, and we want the probability that y is less than or equal to x over 2, given that x is greater than 3/4. All right, so that means that we need f of y given x. And I know it's that order because the P probability statement is y given x. So by definition, this is f of xy, which we have, over f of x, which we may have found on the last handout. Let's go take a look. No, we did not. Okay, so let's go find it this time around. All right, so f of x. Let me do that at the bottom. This is integrating y out. So this is 0 to 1 of 4/3 1 minus xy dy. And this is, again, the integral that you want to evaluate in order to get your PMF or PDF in this case. let me just think through. So this probability is equal to the probability that x is greater than 3/4 and y is less than or equal to x over 2 divided by the probability that x is greater than 3/4. And that is just from your definitional form of conditional probability. So we want the probability that x is greater than 3/4, which we will be able to get to with our marginal. So let's get our marginal. So this is 4/3 y minus x y squared over 2, evaluating y from 0 to 1. And that is going to give us 4/3 1 minus x over 2, where x has the support from 0 to 1. And this is problem 3. So we want the probability that x is greater than 3/4. So let me just check that that's what I had written in the problem. Yeah, x greater than 3/4 is going to be our denominator. So let's go ahead and get that. So this is going to be the integral 3/4 up to 1, because again, that's the support of x. And since this is a probability with respect to the random variable x, we could use the marginal distribution of x, which we just found. And that is 4/3 1 minus x over 2 dx. So when you integrate this, you get 4/3 x minus x squared over 4. And that again is evaluated from 3/4 up to 1. So the x term is going to be 1 minus 3/4, which is 1/4. And then the x squared term is going to be 1 squared, which is 1 minus 3/4 squared, which is 9/16. So 1 minus 9/16 is 7/16. I'm going to simplify a little bit by multiplying the 4 outside through. So this is 1 minus 7/16, which is 9/16. And you still have the 1/3 outside, which is 7 over 48, or sorry, 9 over 48. Simplifies a little bit. I should have divided through by the 3. And we get 3/16. So remember, this is the denominator. So now we also need the numerator, which is the probability that x is greater than 3/4 and y is less than or equal to x over 2. So that is the probability that x is greater than 3/4 and y is, what did I say, less than or equal to x over 2?
Yeah.
Yeah. And so this is a probability using a joint distribution, which we know that distribution. So this is a double integral of 4/3 1 minus xy. I'm going to integrate with respect to y first, because y's support is a function or dependent on x based on what's in this p statement. So I know it goes from 0 up to x over 2. And x, according to the p statement, goes from 3/4 up to 1. So x has a lower bound, y has an upper bound. This is going to give me the numerator for our probability problem. So let's go ahead and work this out. Keeping our first integral there, we've got 4/3 y minus x y squared over 2. And that is evaluated from y going from 0 up to x over 2. And so when we evaluate this, we have 4/3. Y is going to be x over 2 minus 0, which is x over 2, minus an x over 2 times the y squared term is x squared over 4 minus 0. So x squared over 4. And this simplifies a little bit. I'm going to multiply that 4 through in the numerator. So I'm going to have 1/3 times 2x minus 1/2 x cubed. And then from here, I integrate. So I've got the 1/3, and then 2x is x squared minus, then we've got x to the 4th over 8. And this is evaluated from 3/4 up to 1. So at 1, this is 1 minus 1/8, minus at 3/4, this is 9/16, minus 81 over 16, was it 256 times 8? 2048. Yeah, I think I've got everything in there. And what does that give us? So 1 minus 1/8 minus 9/16 plus 81 over 2048 times 1/3. So this is about 0.11735. And specifically, if you wanted an exact fraction, that's what it equals. Which means that this probability statement is going to be 721 over 6,144. That's the numerator probability. divided by the denominator probability, which we got to be 3/16. And this simplifies to 721 over 1,152, which is about 0.6259. So this was a case where because we had intervals in our conditional probability, finding the numerator and denominator separately was easier than getting your conditional PDF first. We still have time, so I'm happy to continue with more problems, but having gone through 3 so far, any questions up to this point? And I realize you may just want to see more examples, but I figured I'd pause for a moment.
Can you go down to the bottom again? I hadn't finished looking at it.
Over here?
Yeah.
Sydney, is there a question, or you just didn't get to copy everything?
I didn't really understand that well, the 2B, you did all that kind of work on the side, and I know it was finding the marginal. I just didn't really understand what you were doing aside from that.
Oh, wait, you're talking about problem 2?
Yeah.
Oh, that's this part.
Yeah. I don't know, it was kind of wild.
Yeah, so this was thinking through a bit more what the PMF should be, because with the way I initially did it, Y's support still depend on X. So I need to investigate further, because it wouldn't make sense to have Y depend on X when the marginal distribution is supposed to have gotten rid of X already.
Wait, so you said Y depends on X?
Yeah, up here. Y goes from X up to 9. But when you sum out X, you've already accounted for when X is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So then which X value should X take when you've used all of them? And so I had to think through what makes sense. And it turns out for each X, the probability is going to simplify to 1/10, which is what I saw here. That when X is 0, this simplifies to 1/10. When X is 1, this simplifies to 1/10. This is 1/10, 1/10, 1/10. All of them simplify to 1/10. So that's how I recognized that G of Y is going to be 1/10, and Y has to go from 0 up to 9. There has to be 10 Y values.
Wait, so if you did X equals 0 to X equals 9, it all simplifies to 1/10?
It does when you account for y also. So this is looking at how the joint distribution is simplifying.
Okay. Well, you're accounting for the joint distribution.
Yeah, because that's what's happening at the top here is I'm checking that the joint, what I thought was the joint distribution is actually a valid distribution, and it is. So what I had determined and the supports I wrote work out so that the double summation equals 1. All right, but we have just under 20 minutes left. So let me continue with the next problem. And, you know, if Sydney or anyone else has questions on this or anything else, we could, you know, I'd be happy to stay a little longer afterwards. But I want to take a look at 4. Yeah, we're on 4 here. So this is related to another problem that we had in the last handout. And so it's the joint distribution of 2, where x is less than or equal to y, and they're both bounded between 0 and 1. We found the marginal distributions on the last handout. I'm just reporting them again here. And we want to determine the conditional distributions of fx given y and fy given x. And so this is maybe the most straightforward problem that we have on this handout. So here we're actually going to use the distributional functions or definitions, which means that f of x given y by definition is the joint distribution over the marginal of y. The joint distribution is 2, and the marginal of y is 2y, which happens to simplify to 1 over y. Now, keeping in mind this is a distribution of x, because y is being conditioned on, so y is no longer random. The support here is that x is between 0 and y. For the other one, f of y given x, it's still the joint on top, the appropriate marginal on bottom. The joint distribution is 2. The marginal distribution of x is 2 times 1 minus x, which simplifies to 1 over 1 minus x. Anyone have an idea what the support of y is here?
Is it x to 1?
Mm-hmm. It is. Yeah, so here x is no longer random. You're conditioning on it. And we know that the original support had 0 less than or equal to x, less than or equal to y, less than or equal to 1. So we want to know the support of y for this second conditional probability or distribution. And y is bounded above by 1 and below by x, because now x is some value. We don't have its value. It's not random, but we could be given that value. And that distribution would hold. And that's your answer. So 4 was pretty quick. We've got one more problem, and it looks like we've got time to possibly finish this. So let's take a look at this one. This is a new one. I don't think we've had this on a past handout. we're given a joint PDF or possible PDF of fxy equals cx times 1 minus y, where y is between 0 and 1, and x is between 0 and 1 minus y. So x is dependent on y according to the supports. In part A, we want to determine the value of c that makes the function a valid PDF. So we need to check the two conditions. One is that the joint distribution is non-negative, being that y is always positive, or at least, yeah, it's always positive because y has to be greater than 0 and less than 1. We know that 1 minus y is going to be positive. And being that x is dependent on y, and y is always going to be between 0 and 1, we know that x will always be positive. So x times 1 minus y is always positive. So we know that c has to be a positive value. Otherwise, f will be negative. Then the second condition is that the area under this function, this curve, has to be 1. So let's check that in order to figure out what c needs to be in order for that condition to be satisfied. So we want the double integral of cx 1 minus y. I'm going to integrate x first and then y. And I do that because x is dependent on y. Y isn't dependent on x. So x goes from 0 up to 1 minus y, and y will go from 0 to 1. This has to be equal to 1. I'm not going to write that in yet just because I like having that 1 equality at the end. That's just my preference. So when I integrate this, I am going to get integral from 0 to 1 of c x squared over 2, 1 minus y dy. And that x part is evaluated from 0 to 1 minus y. So that is going to be 1 minus y squared over 2 minus 0 squared over 2, which is 1 minus y squared over 2 times the 1 minus y, which is going to be 1 minus y cubed over 2 dy. And if you happen to see how to do this directly, great. Otherwise, I'd recommend u substitution. So I'm going to let u be 1 minus y, which means that du is negative dy. So this integral is equal to negative c over 2 times the integral of u cubed du. If you're not sure where all this came from, the u is 1 minus y is u, so I subbed in u for that and got the u cubed. I pulled the c over 2 out, but dy is negative du, according to what I wrote underneath the long equal sign. And so that's where all the aspects came from. And then integrating this, we get negative c over 2 times u to the 4th over 4. And you could either change the limits of integration or put u back in terms of y. So this is negative c over 8, 1 minus y to the 4th, where that is being evaluated from 0 to 1. So we have negative c over 8. When y is 1, we have 0, minus when y is 0, we have 1. So that's going to be negative 1, which gives us c over 8. And like I said at the start, this has to equal 1 for it to be a valid distribution, which means that c equals 8. Which satisfies the first criteria, which was when I recognized that c has to be positive. And now it is. So then we go to part B, now that we have the complete distribution, and this one wants to know the probability that y is less than x, given that x is less than or equal to 1/4. So I realize that the denominator is going to be the probability that x is less than or equal to 1/4. So I want to find that one first. I could look for the marginal distribution first, but I'll just do this all in one shot. So I know x is going to go from 0 to 1/4, and y I'm going to manipulate here, and I'm going to play with these bounds. And I see that 0 is less than x is less than 1 minus y. I'm going to add y here, but I'm also going to eventually subtract x, but I'll just hold that out for a moment. And now when I subtract x, I've got I have these as my bounds for y. And y, I know, goes from 0 to 1. That's from this part here. So this is going to be my upper bound part. So that means I am going to integrate 0 up to 1 minus x of the joint distribution. So this is 8x 1 minus y. I'm integrating with respect to y first and x second. Notice that the x term and the y term are actually not dependent on one another. So you can break these into two integrals. For example, integrating with respect to y, that 8x I could pull out of that first integral. It's not a required step, but it happens to work out in this one. So I've got 8x, and then the 1 minus y is going to be y minus 1/2 y squared, which we are evaluating from 0 to 1 minus x. And that is (8x). We've got 1 minus x minus 1/2 of 1 minus x squared. That's what that simplifies to. We can factor out a 1 minus x. It might make it a little easier. You could also expand and simplify. And if you do that, this term happens to simplify into x minus x squared over 2. And let's check that. So we had 1 minus x minus 1/2 times 1 minus x squared. So I've got 1 minus x minus 1/2 of 1 minus 2x plus x squared, which is 1 minus x minus a half plus x minus a half of x squared. So I see that my x terms cancel out. And I've got 1/2 minus x squared over 2. Or 1 minus x squared over 2. So that should be a 1. Are you guys getting the same, or if you got something different, let me know.
I thought you said it was 1/2 minus x squared over 2.
It's yes. Thank you. And so that becomes, let's see, that 8 can be divided by the 2, and I'm going to bring that out as 4 times the integral 0 to 1/4 of, that's going to be x minus x cubed dx. And when we integrate this, I've got 4 times, we've got x squared over 2 minus x to the 4th over 4, which evaluating from 0 to 1/4, I've got 4 times 1/4 squared is 1/16 over 2 is 1/32 minus 1/4 to the 4th is 1 over 256 times 4. I'm going to leave that as is for a moment. And that's because I realize it simplifies if I multiply the 4 through. And so this is 1/8 minus 1 over 256, which is 31 over 256. So that is our denominator. Let me just set you up for the numerator. I'll leave that for you guys to do on the side. So the numerator is going to be the probability that x is less than or equal to 1/4 and, or you could use a comma, that it means the same thing here, and that y is less than x. And so in this case, we've got a double integral. Y is going to go bounded above by x, below by 0. X is bounded above by 1/4, and at the bottom 0. And our joint PDF is 8x times 1 minus y. We're integrating with respect to y first and x second. And so this is the integral that you want to solve for. And then you're going to divide that by what I shaded or highlighted in blue, and that'll give you your final answer for this one. I'm going to stop here. It's midnight at my time. So I'm going to stop here for now. We've got one more part left that we will finish on Thursday. And that's it for this handout. I know it's a lot, but you've got a lot of examples that we've gone through. So again, I'm going to hang out for any questions that you may have. Let me stop the video. And we will return on Thursday to continue this and move on to the next topic.